introduce our next speaker, who's Sir Michael Berry from Bristol University. He's a very famous person, so as usual, he needs no introduction, but I shall give one anyway. He's famous for the Berry connection and the Berry phase, which was certainly my first introduction to this whole new field of topological studies, which is thriving so well at the moment. He's has been a Royal Society research professor at Bristol, which is quite a high honor from the Royal Society, and he was knighted some years ago. He has many honors, but I'll just mention the chief one among them, which I believe is the Wolf Prize. And he's now going to speak to us on wave trajectories, quantum potential, superoscillations, de Broglie, Madelung, Bohm, Newton. And if he gets to the end of that, he'll be a lucky man. Thank you, Michael.
Good. Can you hear? Yes. Even at the back? Good. My excuse for speaking about very elementary matters at this lovely meeting where every other talk is much more detailed and sophisticated is that sometimes it can be helpful, or at least interesting, to describe very familiar concepts from an unfamiliar point of view. And that's my theme today, my underlying theme. This talk was inspired, or perhaps provoked, by the fact that this year is a centenary of de Broglie's papers on matter waves. But the real hero of this talk is Madelung, who came along a few years later. But there's a historical anticipation of Madelung by Isaac Newton that I find utterly amazing, and I will get to that in due course. Well, de Broglie, he really was emphasizing the ubiquity of waves of all kinds. He concentrated on massive particles, but of course this was in the context of all the other waves. Madelung came along in 1926, just after Schrödinger's wave equation, and he interpreted Schrödinger's wave equation, and indeed all wave equations, although he didn't emphasize this, in terms of trajectories. Now, this is an optics meeting, so let me describe things in terms of Helmholtz in a refracting medium. Here's a refractive index that may vary with position. He wrote the wave function in terms of its modulus and its phase, and he paid most attention to the gradient of phase. Now, that's an irrotational vector field. The integral curves of this, that is, the curves that are tangent everywhere to this vector, are, in quotes, rays, streamlines, Madelung trajectories, I'm going to occasionally call them, and they're the wave counterparts of the rays of geometrical optics. Many interpretations of this local wave vector: local momentum, local velocity with trivial scaling, current, Wigner function, mean velocity at a given place, the weak value of velocity in a Aharonov scheme. There are many different ways of thinking about this vector field. Now, of course, you have the underlying Helmholtz equation. That tells you two things. One is that the current, the Poynting vector, energy flow, intensity times k, is divergenceless. It's a continuity equation. And then, most significantly, is that this local wave vector, here it is, the length of it is the length that it would be in geometrical optics plus something else. And that something else is the wave analog of what has been called the quantum potential. I should say that what Madelung did was rediscovered later by David Bohm, but it's really Madelung that I'm emphasizing. This is a way of bringing non-locality into the theory, because to find this this modulus, you have to solve the wave equation everywhere, and that determines in particular its value at the place where you are. Good. Now you can think of this as a modified refractive index. So here it is. The modified refractive index is the geometrical one plus this additional wave potential, as I'm going to call it. There it is. Now, it follows very immediately that the analog of the Newton equation for particles, modified by this potential, tells you that the curvature of one of these trajectories is the normal derivative of the refractive index, the modified refractive index, at the normal derivative perpendicular to the ray at that place. So this generalizes what we know from Snell's law in geometrical optics. And it tells us something, that even in free space, where this refractive index is constant, you still have this dependence, so that rays are curved even in free space. There's another condition which is to do with single-valuedness of the wave function, and I won't emphasize it. Now, let's see how this works. Trivial case, two plane waves, different strengths, different directions, two overlapping families of classical trajectories, Newtonian rays, plane waves. And there's an average momentum. Now, if you look at the wave intensity, you see, of course, interference, as it would have been conceived by Thomas Young and Fresnel in those old days. I can't resist quoting Arago, who said, "Who would have imagined that darkness could be engendered by adding light to light?" This was him speaking about Thomas Young. Okay, now here are the trajectories, the Madelung trajectories. They're orthogonal to the wavefronts, and phase I've color-coded and will do throughout this talk. You immediately see a difference between this and the rays of geometrical optics, is that these Madelung trajectories never cross. Now, and that's another way of indicating interference. There are a number of different ways, negative values of the Wigner function, for example, and as I've described, these fluctuations in intensity that I showed a moment ago. But these undulations are a different indication of interference. Why are they so different? And the reason is that phase and phase gradient are nonlinear functions of a wave function, so the superposition of momenta is not the same as the momentum of the superposition. I mean, that's the underlying reason why this is an interesting point of view. Still, it's not the most general phenomenon you can get. You get that with three plane waves. Here are the geometrical rays. But here's the intensity, and you see there are these minima, they're actually zeros. And if you look at the phase, you can see what has often been discussed at this meeting, the phase singularities, wave dislocations, we called them in the beginning, in the 1970s, nodal sets. Now, if you look at the Madelung trajectories, you see that they're closed around the vortices, around the phase singularities. So that's why phase singularities are vortices. Just a different terminology. Okay, now here you are again, looking at a single vortex. Here it is, and you see these closed streamlines. Now, at a vortex, the wave amplitude is zero, and that means that this wave potential diverges. So you can think of these as the waviest places. If it were quantum mechanics, they're the most quantum places, these phase singularities. Again, it's something we emphasize, but from a different point of view very long ago. Okay, some history. The first wave singularities that I know were discovered by William Whewell in the tides in 1833. Now, here's England and here's France, and this is what was called the German Ocean in those days. And each of these curves is a wavefront of the tide wave. Now, what that means is that it connects at a given time all the places where the tide is high. And what Whewell realized, and he was criticized for this by people who didn't understand him, that there has to be a singularity. He called them amphidromic points because as time passes, these wavefronts rotate around, and they're tideless places, places of no tide. By the way, we owe to Whewell the words scientist and physicist, both of which were criticized by linguistic scholars at the time, but we still have these terms, we use them. Now that's Whewell. But in modern oceanography, it's a central concept. In all of the world's oceans, there are these phase singularities in the tide, and they're very helpful in understanding the anatomy of the pattern of the tides across the globe. They're generic in waves of all kinds. They're the stable singularities of scalar wave physics. Polarization is something else, not for today. Now, Isaac Newton actually anticipated Madelung and Bohm, de Broglie, all of that, and he almost discovered phase singularities, and I want to explain that. In edge diffraction, Newton was tormented through his whole life by what we understand as wave phenomena, and this is one of them, edge diffraction, alternations of color in the shadow of an edge. And he conjectured something late in his life, that the edge might exert a force on the rays, and he speculated that are not the rays of light in passing by the edges and sides of bodies bent several times backwards and forwards with a motion like that of an eel? It's anguila in Spanish. Maybe also in Catalan, I don't know. Now, Newton was right, but it took 250 years to see that he was right, and the people who did, it wasn't appreciated that the idea went back to Newton. First of all, you needed Sommerfeld's exact solution of Maxwell's equations for an electromagnetic wave diffracted by a half plane. That's deconstructing shadows. And the formula doesn't matter, but it involves Fresnel integrals. Okay. Now, what Newton wanted to understand was that if you look at a screen, if you look at a screen, you see these oscillations. And that's where he conjectured about the bending of the rays. Now, it wasn't until 1952 that Braunbeck and Laukin plotted what I'm calling the Madelung trajectories, with the curves of the pointing vector. And again, they didn't realize that they were actually confirming Newton's speculation. But here, we come to this part in a moment, here you see precisely Newton's eels. It's quite easy to do these calculations now. Now, even more astonishing, Newton said, do not the rays begin to bend before they arrive at the bodies? Well, yes, they do. Here we are. So Newton anticipated Madelung, but and the force that he envisaged was just minus the gradient of the Madelung's wave potential. It's all there. But there's no evidence that he thought that these forces could be strong enough to cause the trajectories, the rays to close. But they are, and if you look at the region ahead of the screen, you do indeed see these vortices. And you can zoom in and you can interpret, you can understand using asymptotics that these result from perfect destructive interference of three waves. There's the incident plane wave, the approximate plane wave reflected by the screen, and a Thomas Young edge wave from the top. So that's Isaac Newton. I wonder how many other time bombs he has waiting for us to suddenly realize that he understood something in some sense that we only fully appreciated much later. Now, I want to discuss this wave potential and its connection with geometrical optics. You see, from these formulas, the short wave limit, which should be geometrical optics, is large k, k0. And it might seem from this formal limit that semi-classical, if it's quantum, that vanishing wave potential corresponds to geometrical optics, places where this potential is zero. Well, actually, that's not the case. It's wrong because for all non-trivial waves, this modulus also involves k0, and in a very complicated way. I mean, the dependence is highly singular, and for example, it represents rapid oscillations. And this is a a large subject. I mean, geometrical optics is a singular limit, and it's a very long story. There are many aspects to it, which I won't go into. Decoherence, quantum chaos, diffraction catastrophes, divergent series, another day. The real significance of vanishing places where this potential vanishes involves superoscillations, and that's also been discussed a couple of times, so I'll be very quick. These are functions that vary faster than they should. A band-limited function, here it is, finite range of its Fourier content. Conventionally, it has a fastest oscillation corresponding to the fastest, largest Fourier component. But nevertheless, and counterintuitively, such functions can oscillate arbitrarily faster than their fastest Fourier component, and they can do so over arbitrary long ranges. It's not paradoxical, as where they do this, they're extremely small. But nevertheless, this happens, and it's much studied, and it was mentioned in the talk by Nikolai Zaludev, emphasized, and I won't go into details. But except to say that a measure of superoscillations is how fast the phase is varying, and that's the length of the local wave vector. It varies from place to place. Now, for the moment, think of Helmholtz in free space. This is band limited. The solutions are superpositions of plane waves, all of which have the same wavelength, same length of wave number. And superoscillations are where the local wave vector is longer than the wave vector of all the plane waves that superpose to make up the complicated wave that you're looking at. Here's a superposition of 10 plane waves. Here's the intensity. Here's the phase and the Madelung streamlines, of course, going around the vortices. Very strong superoscillations near the vortices because, as I've explained already, the intensity 0, the wave potential is very large. If I just look at the region of superoscillations, it's surprisingly large, and it of course always includes the vortices, and Mark Dennis showed that for typical random waves, a third of the area is of the pattern is superoscillatory. Now, what's the connection with the wave potential? Well, here's Helmholtz with refractive index unity for simplicity. Here's the wave potential. Now you see that when it's 0, you're on the boundary of the region of superoscillations because the local wave number equals the wave number of all the plane waves. So this is the significance of places where, of the set of places where the wave potential vanishes. So there it is. Now, by the way, in the superoscillatory region, the wave potential is negative because this K local is greater than K global. Very good. Now, this might seem to be of limited use because if you have a potential or a refractive index, a potential in quantum mechanics, then the solutions, waves are not band limited. So what becomes of superoscillations? Well, Pragya Shukla and I recently realized that actually you can generalize the concept. Local oscillations are faster than geometrical optics would allow. So in very simple, the local square is greater than the geometrical wave number squared times the refractive index squared. And in quantum mechanics, the counterpart is it's greater than the classically allowed momentum. Now I'm going to show you an example of that. Falling waves. Imagine the refractive index varies linearly. Then the solutions, I've scaled away some trivial constants, are superpositions of airy functions with different sideways momentum. And this is the along the variation of the refractive index dependence. Geometrically, this corresponds to a family of parabolic rays. It's an upside-down mirage. Well, superoscillations are where the local length of the wave vector is greater than minus the y that's in the refractive index. Here's a simple superposition, just two of these waves. And here I've shown you the wave where I've shown you only the regions where the wave is superoscillatory in this generalized sense. And of course, in the forbidden region, up here in the evanescent wave region, it's superoscillatory, but also elsewhere, and that's a consequence of interference between more than one geometrical ray or classical path that would cross. You can make up random superpositions, n of them with random phases, and you get nice patterns. And then you can do some statistics. You can ask, what's the probability at a given depth y that the wave is superoscillatory there? Well, the probability goes to 1 when you reach the boundary, but also it non-trivial below. And when you go far below, it oscillates around the value 1/3 for a typical random wave in a uniform medium. So that's understood. Just one final thing that, we have plenty of time. Just one final thing. I've said that the streamlines are closed around vortices. That's not true if you for approximate waves. And one of the most common approximations that we all consider, often without even thinking, is paraxiality. And when you have paraxial waves, the wave number, it doesn't satisfy a continuity equation as it does for Helmholtz, and a consequence of that is there isn't an underlying stream function whose contours are the trajectories. So, for example, if you have a propagation direction y, then you, in paraxial optics, you separate out the y dependence from the transverse dependence, which can be one or more dimensions, and then you can approximate this by in the case of waves which are all plane waves traveling almost in the y direction. And here's an example, Pearcey function of x and y. So this is one-dimensional transverse and longitudinal y. Here's x, here's y. And this, here it is. Its significance, it's quite a common observed function, wave in optics. It describes diffraction near a cusped geometrical optics caustic. And well, here you see all of these regions of low intensity, and it's an exact solution of the paraxial wave equation. But when you look at the Madelung trajectories, here they are, you see that they're not closed, they spiral. Let's look in more detail at one of them. You see, here they are. Now, these spirals are very tight. Long ago, when I realized this phenomenon, I calculated how they spiral. And if you're a distance r from the vortex, the radial distance between successive windings gets smaller as r cubed. So they really are, I mean, if you just look experimentally or not well-resolved numerics, you would think they are closed, but they're actually not. So that's just something to be aware of. The geometry of these Madelung trajectories does depend on which wave function, which wave equation your wave that you're interested in satisfies. Very good. Now, I want to conclude. These Madelung trajectories enable alternative understanding of familiar phenomena and connections between a number of different concepts. And here they are. I mean, velocity streamlines, undulations indicate interference, Newton's eels, this historical anticipation, wave vortices, these points, vanishing of the quantum potential and connection with generalized superoscillations, and these paraxial streamlines need not be closed. I just want to emphasize the ubiquity of these phase singularities. As I'm speaking to you now, the sound waves in this room, bouncing around among you and off the walls, are threaded with a forest of acoustic phase singularity lines. They're threads of silence, and they move past your ears too fast for you not to hear them. So just to, they really are ubiquitous. Now, there are a number of matters I could have discussed more. This subject is much more extensive than I've indicated, and I've just mentioned one or two of them. Mark Dennis and I, long ago, showed that these vortices, well, they're zero according to Maxwell's equation or wave equations, but actually they're windows down to which, with a suitable arrangement, you could see the ceaseless fluctuations of the quantum vacuum. So, for example, if you have an excited atom and you put it there, it's what Mandel called a quantum counter, you can do the quantum mechanics, and you find that, of course, mostly this atom will decay by stimulated emission of the wave that's there. But when that wave is zero, there's no stimulated emission, but of course there's always spontaneous emission. And there's a zone, which we call the vortex core, which is the zone within which spontaneous emission dominate into other states which don't have a zero there, we dominate over the stimulated emission, which is what you expect caused by the wave that you started with. So these are quantum cores. By the way, they're also acoustic cores, where the physics is different. But if you have a sound wave, and the usual assumption that air is a continuum, which we all assume, but of course you know it isn't, and there's Brownian motion. So on any detector, for example, your eardrum, or a microphone, any detector, there's a size around one of these acoustic vortices, which we've calculated, a size, a region where you'd hear the Brownian motion. Our ears are so arranged that you don't quite, otherwise it would be, you'd hear Brownian motion all the time. But anyway, you can calculate the width of this acoustic core. Miles Paget thinks he's measured it using a microphone, but I'm not quite convinced it isn't noise in the circuitry that he's using, but that is unresolved. Then there's something else. For example, if you take seriously this idea that the K vector represents momentum in the optical field, then this was work with Stephen Barnett. If you put an atom there, it could be kicked with momenta corresponding to this local wave vector length, and this momentum near a vortex is much larger than any of the momenta in the plane waves that make up the superposition. Now that sounds paradoxical until you realize that the intensity diminishes there, so these super kicks are very rare. And if you take the average over time of their rareness together with their strength, you get precisely what in old terminology we called radiation pressure. So the outcome of that it's a proper quantum calculation. The atom is a two-level system, and you look at the momentum distribution after it's made a transition. Is that radiation pressure near a vortex deconstructs into extremely large, extremely rare super kicks. So that's something which it would be very nice to see. So this subject goes on, and there are many other developments of it. Okay, and I haven't even discussed polarization singularity. It's another story. So let me finish by quoting Charles Frank, because this is really all about connections. And he said, physics is not just concerning the nature of things, but concerning the interconnectedness of all the natures of things. Thank you. Just to say, if there are questions, I don't hear very well, so I might ask John to...
Okay, I don't hear very well.
Use a microphone ananyway. He has the same problem.
Reading the slide. I think your hand was up first.
Thank you for...
I think you should please use the microphone. It will come to you now. Otherwise, even though you have a loud voice, people might not hear you.
I think my voice carries enough. Thank you for your presentation. I wanted to comment on it. I know a lot of the people in here take inspiration and instruction from you, and I firmly believe that they should take instruction from the way you present as well. It's a very difficult thing, these fundamentals, especially for someone kind of outside the field, like myself. But you presented it in a very followable way that I appreciate. Your story about, or this story about Newton reminded me of an old supervisor that I had. When I told him that I couldn't find something in the literature, he would say that everything has already been observed in nature or mathematics and physics. So continue to dig, basically, is what he said. I wanted to know what you think about that.
I have to quote Simon Sharma. Simon Sharma is a historian, and he's often on the television. And I once went to a lecture, and after the lecture, the chairman asked for questions, and someone like yourself was saying some extremely nice things. And after some time, Simon Sharma said, "You're obviously a very nice man. You're also a very nice young man, and thank you for these comments. Unfortunately, my daughter is already married." Now, you can't beat that. But seriously, I mean, you know, having observed a phenomenon is different from having understood it. So your comment about being observed is not quite to the point. But of course, you can find anticipation sometimes and sometimes not in the literature. And those people, our predecessors who we admire them because they were far ahead of other people and mostly vastly cleverer than we are. So there are things that they glimpsed which weren't appreciated until now. Now this is something that causes friction between physicists and historians. You see, we like to find things, our modern concepts anticipated by people in the past. Historians hate this. They have a name for it. They call it Whig history, and there's a reason for that name. Meaning, they say you must never interpret the past in terms of the present. You have to confine yourself to sources available at the time. And I think it's an interesting exercise, and it's legitimate scholarship, but it's unnecessarily restrictive, because we revere those people and remember them precisely because of what their work has led to today. So thank you for that comment.
Thanks very much.
Yeah.
More questions, please. One at the back there.
Thank you for talk. So you mentioned this phase singularity. Can we generalize this to quantum mechanics, like a quantum singularity?
Oh yes. At the same time as John and I were writing our paper in 1974, there were papers by Joseph Hirschfeld and his colleagues in quantum chemistry who looked at various quantum scattering scenarios and found phase singularities in the waves there. So the answer is yes. And nowadays, of course, people make, and it was mentioned in the talk by Ido Kamina, nowadays people are finding or creating and using vortices in electron waves.
Okay, then what's the implication for this quantum singularity? Is it something like Anderson localization? You have some?
No, it's not. It's not to do with Anderson localization. Is a phenomenon of multiple scattering, and this is only in the loose sense that both are phenomena of coherent destructive interference. But Anderson is to do with disorder, and this is phase much more general. I mean, they do occur in random waves, but they also occur in non-random waves. In fact, almost any wave that's a solution of a wave equation, linear or non-linear, which is not just the simplest plane wave or circular spherical wave, has phase singularities in it. Yeah.
Thank you.
Michael, the boundaries of the superoscillations.
Yes.
So if you go inside these boundaries, can you tell us something about the intensity of the waves there, as well as their superoscillations?
No, not in general, but very often these boundaries are caustics, where in the opposite limit of geometrical optics, as opposed to this fine structure that we're looking at, the wave intensity would be infinite. But that doesn't correspond to every such boundary, but it's a common feature.
Of course, if you had superoscillations and high intensity,
Yes.
they would be very good candidates for super resolution.
Oh, well, indeed, and that's again a long story, and you can think of it as underlying what Nikolai Zaludev told us about, because you're using superoscillations. Now, it would be a good candidate, except that right, now I'm thinking clearly. Superoscillations occur in places, I mean, strong superoscillations where you want to use, they occur in places where the wave is very weak, and that's how you evade the uncertainty principle, of course. So the answer is, in general, there are not high-intensity superoscillatory regions on the boundary, but then you only get a little bit of superoscillation, so you wouldn't get very much super resolution.
I see.
Indeed, it's a problem, and he mentioned it in response to some of the questions, that if you want to push this wonderful superoscillatory microscopy that he studies, if you want to really push it, in principle, to get higher and higher, to resolve smaller and smaller things, you have to reckon with the fact that away from the superoscillatory region, the wave is very intense and can burn your sample. And that's what he discussed.
Exactly.
Yeah.
Yes. So there's no particular relation between the intensity and the phase. No. I see. No. Yes, thank you. Javier, I think your hand came next.
He's coming.
Yeah. Let me start with a disclaimer that I'm not particularly interested in your daughters, but I still find your talk really inspiring, really, really inspiring for all of us. I was wondering about the 1/3 feeling, partition of this supersolitary behavior. Why 1/3? I was puzzled by that. Is there any clue about that number?
I'll tell you, it depends on the number of dimensions. And after Mark Dennis found this basic result for planar speckle fields, for example, described locally approximated by Gaussian random functions of position. If you look, we generalize it to d dimensions, and roughly speaking, if you go from 1 to infinitely many dimensions, it changed from about 0.3 to 0.4. And then for 2 dimensions, it's a calculation, and it's just to do with the
but it can change to...
It's an integral. I can't immediately tell you why it has to be a third, but it is.
So depending on the dimensions, it would be another number, or...
Yeah, as I said, it's between about 0.3 and 0.4, so it doesn't vary very much with dimension.
But it's still what bounds this 3,
it's still
4.
larger than you think. That's the point. It's larger than you think. And the boundary, which I described in now thinking more intelligently about John's question, is only slightly superoscillatory. I mean, you go just inside. But in the vortices, it's infinitely superoscillatory, because the wave vector is infinitely long, because the phase has to change by 2 pi around a smaller and smaller loop, and so that the phase is very, very fast. Yes. So, yeah.
Okay. Here, then here. So first.
If we imagine non-stationary wave and phase singularity will move and collide, is it possible to introduce effective interactions? How will they interact?
Sorry, I don't understand. Say it again. What are you asking?
If phase singularities move in time.
Move, yes.
Yeah, and how they interact.
Yes, thank you. Here's the point. If you have a time-dependent wave equation, and that's what John and I originally studied, actually, then there's no limit on the speed. Even though you have a normal causal Maxwell equation, the phase singularity can move at any speed, even faster than light. Their forms are not things, so they don't carry energy or mass with them. So the answer is yes, they can. And when they coalesce, which they can do as time passes, they move infinitely fast at the moment of coalescence. So, and that's important. It means you can't use them directly to form images, but you can use them, and Nikolai Zaludev talked about this, as very sensitive indicators of changes in a diffracting object. So thank you for that.
Yeah, but so they attract and coalesce. They not repel each other. So
Say?
So effective interaction is attraction and coalescence. So
well, it's interesting. I mean, we originally thought of them as analogous to, and indeed they are morphologically, to dislocation defects in condensed matter, because they're analogues of edge dislocations, screw dislocations. The analogy is only kinematic. There's no dynamical, no mechanical. Now, with certain nonlinear equations, you can think of forces between the vortices, but this becomes less significant as they approach, because every nonlinear equation is linear near its zeros. So the answer is there's a kinematic analogy, but you shouldn't push it too far and think of a dynamical analogy. Good. Yeah.
One last quick question, I hope, from Javier.
Okay, so I've been always intrigued by these super oscillations where you can make the oscillation as small as possible.
Yes.
But you pay the price that you reduce the intensity, and then you have these sidebands.
Yes.
Maybe it's useful when you have edges or something where
Yeah.
the sidebands don't play such a role. But for example, if you have in free space and you want to detect one atom, then you don't worry about melting materials or things like this. And so even the Broglie wavelength, coming to some elements of your talk, is something you might want to resolve. Is it true that you can resolve that with light without restriction of the wavelength?
This has been developed in great detail by Nikolai Zaludev, and is what he spoke about. I mean, and the basic reason why it works with light is that photons are cheap. So you can, although the intensity gets very small there, you can make it larger and larger. You do have to worry about burning your samples, and that's important if it's a biological object that you're looking at. But yes, I'm very reluctant to use the word in principle, because it often conceals more than it reveals. But still, underlying your question, in principle, yes.
Thank you. Thank you, Mike.
Yeah.
Let's give Mike another round of applause.
Yeah,